Welcome to the Deep Dive. We're here to take a whole stack of information, find the core nuggets, and get you well-informed fast. Today, we're diving into the fascinating world of chemistry, specifically the periodic table and those incredible trends that make it so powerful. You sent over a ton of material from a Gen Chem textbook. Our mission: cut through the complexity, highlight the essentials about how elements behave.
Exactly. It's really a journey through the fundamental patterns governing matter itself. We'll look at how the elements were first organized, what defines their unique character.
And why their properties change so predictably as you move around the table.
Yes, across or down. We'll touch on atomic radius, ionization energy, electron affinity.
Okay, yeah, and even why some ions can mimic others in your body.
Yeah.
Get ready for hopefully some aha moments.
Absolutely.
Okay, let's unpack this. So our journey starts back in the 19th century. 1864, a chemist, John Newlands, noticed something kind of cool. If you arranged elements by atomic mass, every eighth element seemed to share properties. He called it the law of octaves. Sounds simple.
It was a good first observation, definitely. But his law, well, it had limitations, especially once you got beyond calcium. The real breakthrough, it came independently in 1869. Dmitry Mendeleev and Lothar Meyer, they both proposed this idea of periodicity.
Periodicity, so the regular recurrence of properties.
Exactly.
And here's where Mendeleev gets really interesting, all right? He didn't just group the 66 known elements.
No, he famously predicted the properties of elements that hadn't even been discovered yet.
That's incredible. He left gaps in his table for them.
Yes, his prediction for Ica aluminum, which later turned out to be gallium, was just spot on. Density, melting point.
Wow.
It was a monumental achievement. It really showed the predictive power of his table,
Yeah.
made chemistry feel much more like a solid science.
But even his brilliant work had, well, inconsistencies like argon and potassium. Argon comes first on the table now, but it has a higher atomic mass than potassium.
Right. If you just ordered by mass, it didn't quite work. You'd have sodium, a metal grouped with gases, or argon, a gas with metals. It felt wrong.
So what was the missing piece? What really determines an element's place?
That question led to Henry Moseley in 1913. He was studying X-rays generated by elements.
Okay.
And he found this direct correlation between the frequency of those X-rays and the element's atomic number, the number of protons.
The protons, not the mass.
Exactly. So ordering the table by atomic number instead of atomic mass cleared up all those discrepancies, like the argon-potassium problem.
And that's why modern tables use atomic number and electron configuration. It lets us predict properties so accurately, like you see chlorine in group 7A.
And you expect fluorine, bromine, iodine below it to be pretty similar, which they are mostly.
Yeah.
Though you still have to be a bit careful comparing, say, a non-metal like chlorine to a metalloid like astatine down at the bottom. Similar, yes, but not identical.
Right, nuances. Okay, so armed with atomic number, let's look at the modern table. How do we classify these elements?
Well, primarily you have the main group elements. Those are in groups 1A through 7A.
Got it.
Then the noble gases in group 8A, famous for being, well, noble, unreactive. Their outer electron shells are completely full.
Stable. And then the transition metals, those middle blocks.
Right, groups 1B and 3B through 8B. They typically have incompletely filled D subshells. That gives them interesting properties like color, but a small detail.
Yeah.
Group 2B zinc, cadmium, mercury, technically, they're D block elements, but their D subshells are actually always full, so they aren't always strictly called transition metals by everyone. Depends on the definition you use.
Okay. Good distinction. And those two rows at the bottom.
The lanthanides and actinides, often called the F block transition elements, they have incompletely filled subshells. They're quite similar to each other within each series.
What really stands out, though, is that pattern in electron configurations within a group. Like you said, group 1A always ends NS1, group 2A, NS2. It's so neat.
It really is. And that regularity points straight to the importance of valence electrons.
The outermost ones.
Yes, the ones doing the work in chemical bonding. The reason elements in the same group have similar chemical properties, it's because they have the same number and type of valence electrons. It dictates how they interact.
Okay, now let's get into what drives these trends. You mentioned something called effective nuclear charge. Sounds important.
It's absolutely crucial. Effective nuclear charge, we call it Z-effective or ZEF. It's the actual positive charge an electron feels from the nucleus.
Feels like it's not the full charge.
Exactly. In atoms with more than one electron, the electrons are attracted to the nucleus, sure, but they also repel each other. This causes shielding.
Shielding. Like a barrier.
Precisely. The electrons closer to the nucleus, the core electrons, are pretty good at shielding the outer valence electrons from the full positive pull of the nucleus.
Okay, so they block some of the attraction.
Right. Now think about what happens across a period, left to right. You add protons, so the actual nuclear charge, Z, goes up, but you're adding electrons to the same outer shell. The number of core electrons stays the same.
Ah, so the shielding doesn't really increase much, but the nucleus gets stronger.
You got it. So Z effective increases steadily across a period. The outer electrons feel a stronger pull. Now, down a group.
Down a group, you add a whole new shell.
Exactly. So while the nuclear charge Z goes up a lot, you're also adding a whole new layer of core electrons, which are very effective at shielding. So the Z effective doesn't increase nearly as much going down a group as it does going across.
Okay, that makes sense. Like with helium, removing the second electron is way harder than the first.
Perfect example. Once the first electron is gone, the second one feels the full, unshielded +2 charge of the nucleus. No shielding left.
Okay, Z effective. Got it.
Yeah.
So how does this explain the big trends? Let's start with atomic radius, the size of the atom.
Right. So atomic radius increases as you go down a group, top to bottom.
Because you're adding shells further out.
Exactly. Higher principal quantum number n, electrons are simply farther from the nucleus. Makes the atom bigger. Pretty straightforward.
But then it decreases from left to right across a period. That's the tricky one. You're adding electrons, but it's smaller.
That's Z effective in action. As you move left to right, Z effective increases, remember. That stronger pull drags the valence electrons in that same shell closer to the nucleus.
Even though there are more electrons repelling each other.
Even so, the increased nuclear attraction wins out. Think Coulomb's law. Force increases with charge, decreases with distance. Higher Zeph pulls those electrons tighter. So yeah, more electrons, but a stronger pull shrinks the overall size.
So if you compare, say, phosphorus, sulfur, and oxygen, oxygen's highest up and furthest right of the three. It's smallest.
Oxygen is smallest, yes.
Okay.
Then sulfur, because it's below oxygen, and phosphorus is larger than sulfur because it's to the left.
Okay, makes sense. Next trend, ionization energy. The energy needed to remove an electron.
Yes, specifically from a gaseous atom to form a positive ion, a cation. How hard is it to steal an electron?
So harder across a period because of Z effective.
Generally, yes. First ionization energy, IE1, increases left to right. Electrons are held tighter, takes more energy to remove one, and IE1 decreases down a group.
Because the electron is further away, easier to grab.
Right, weaker attraction. But there are little dips.
Yeah, you mentioned those. Why is group 3A lower than 2A? Like aluminum lower than magnesium.
Ah, electron configuration again. In group 3A, you're removing the first electron from a p orbital. In group 2A, it's from a filled s orbital. That p electron is slightly higher in energy, slightly further out on average, just a little easier to remove.
Okay, so the orbital type matters. And what about group 6A being lower than 5A?
Similar idea, but about pairing. In group 5A, like nitrogen, you have 3 electrons each in separate p orbitals. Very stable half-filled arrangement. In group 6A, like oxygen, you have 4 p electrons, so one orbital has a pair.
And electrons don't like sharing space.
Exactly. That electron repulsion within the pair makes it slightly easier to remove one of those electrons compared to removing one from the nice, stable, half-filled configuration in group 5A.
Fascinating little details. And it always takes way more energy to remove core electrons, right?
Oh, absolutely. Orders of magnitude more. Look at sodium. IE1 is reasonable 496 kJ-mol, but IE2. Removing a second electron, that means breaking into the stable, noble gas core, jumps to over 4,500 kJ-mol.
Wow. Okay. Last big trend. Electron affinity. This is about gaining an electron.
Yes, the energy change, usually released when a gaseous atom accepts an electron to form a negative ion, an anion. How much does it want an extra electron?
So generally increases across a period too. More positive Z effective attracts an electron more.
Generally, yes. Becomes more favorable, more energy released from left to right.
Yeah.
Again, exception.
Let me guess. Group 2A and 5A again.
You got it. Group 2A elements have low electron affinities. Adding an electron means putting it into a higher energy p orbital, which isn't favorable.
Costs energy, sort of.
Right, and group 5A, adding an electron means pairing it up in a p orbital, just like we saw with ionization energy. That repulsion makes it less favorable than adding an electron to group 4A.
Okay. And you said the first electron affinity can be favorable, release energy, but adding more after that.
Subsequent electron affinities are always unfavorable, always require energy input. You're trying to force another negative electron onto an already negative ion. They repel strongly. Oxygen, gaining one electron, releases energy, Ea1 is positive. Gaining a second to make O2 costs a lot of energy, Ea2 is negative.
Right, that makes sense. And all these trends together explain metallic character, don't they?
They absolutely do. Metals on the left and bottom have low ionization energies. They readily lose electrons, form positive ions. They're shiny, malleable, conduct electricity.
While nonmetals, top right, have high electron affinities, high ionization energies. They tend to gain electrons or share them, form negative ions or covalent bonds. They're often brittle, poor conductors.
And metallic character increases down a group, easier to lose electrons as atoms get bigger. Decreases across a period, harder to lose, easier to gain as Z effective increases. It all ties back to Coulomb's law, charge, and distance.
This electron configuration stuff also helps predict the ions that form, especially for main group elements. They want to be like noble gases. That's the key driver for many of them. They gain or lose electrons to achieve that stable, filled outer shell configuration of the nearest noble gas. We say they become isoelectronic with that noble gas. So sodium, group 1a, loses one electron, becomes Na plus A, isoelectronic with neon. Chlorine, group 7a, needs one, so it gains one.
Cl, isoelectronic with argon. Simple. But what about the transition metals, the D block? They don't usually reach a noble gas configuration, do they?
No, they behave differently. When a transition metal forms an ion, it always loses electrons from the outermost shell, the one with the highest principal quantum number n first, usually the s electrons.
Even if the d electrons were added last when building up the atom?
Yes. It seems counterintuitive, but once the atom is formed, those n's electrons are effectively the outermost. So iron F, for example, its configuration ends in 4s2 3d6. To form F2 plus A, it loses the two 4s electrons, not the third.
Not first. To form F3 plus A, then it loses one of the third electrons after the 4s are gone.
Okay, that's a crucial rule for transition metals. And when atoms become ions, their size changes, ionic radius.
Right. Cations positive ions formed by losing electrons are smaller than their parent atoms.
Less electron repulsion? Maybe lost an entire shell.
Both can contribute. Fewer electrons means less repulsion, pulling them tighter. And if the outermost shell is emptied, the size drops significantly. Sodium atom versus Na plus ion is a classic example. Huge difference.
And anions, negative ions formed by gaining electrons, are larger than their parent atoms.
Yes. Adding electrons increases the repulsion in the valence shell, causing it to expand or puff out. Chlorine atom is smaller than the Cl ion.
This leads to the idea of an isoelectronic series. Same number of electrons, different number of protons.
Exactly. Like, say, O2F, Na plus Cm, Mg2 plus side. They all have 10 electrons, same configuration as neon.
But different nuclear charges. So how does that affect their size?
The one with the most protons will pull that electron cloud in the tightest, making it the smallest ion. The one with the fewest protons will have the weakest hold, making it the largest.
So in that series, Mg2 plus 12 protons would be smallest, and O2, 8 protons, would be largest.
Precisely. The more positive the nucleus, the smaller the radius for the same number of electrons. You could look at another series, maybe K plus S, Cl, S2P3, all have 18 electrons, like argon.
Okay, so K plus has 19 protons, Cl has 17, S2 has 16, P3 has 15. So K plus is smallest, P3 is largest.
You've got it. K plus CLS S2P3 in terms of increasing radius. Fewer protons means a larger ion for isoelectronic species.
And this isn't just textbook stuff. You mentioned a real-world example, something about bones.
Yeah, it's quite relevant. Your bones need calcium, K2 plus ion, but strontium, which is right below calcium in group 2A, forms an SR2 plus ion. Chemically, they behave very similarly because they're in the same group. Unfortunately, radioactive strontium-90 is a product of nuclear fission. If it gets into the environment, your body can mistake SR2 plus for Se2 plus because they're so similar.
So it gets incorporated into your bones instead of calcium.
It can, yes. And having a radioactive element embedded in your bones is obviously a major health concern. It's a stark reminder of how these fundamental properties, group similarity, ionic charge, radius, have real biological consequences.
Wow. Okay, so we've really covered a lot. From how the table was built, piece by piece,
to understanding Z effective as the driving force behind the trends.
Atomic radius, ionization energy, electron affinity, metallic character.
And finally, how ions form and how their sizes compare. It all fits together quite elegantly.
Understanding these periodic trends, Z effective, i.e. Ea, it really is fundamental to predicting how chemicals will react, isn't it?
Absolutely. It's the foundation for so much of chemistry. It gives you predictive power.
So next time you look at that periodic table, hopefully you'll see more than just boxes with letters. You'll see a dynamic map, a system of interconnected properties.
Indeed. And maybe something to ponder for you. Consider this. What if shielding by core electrons was, say, perfectly efficient? What if they blocked all the nuclear charge except for a +1 effective charge for every valence electron?
Perfect shielding.
How would that change the trends we just talked about, especially going across a period? What would that imply for, well, the diversity of chemistry itself?
Interesting thought. Something to mull over as you continue your own deep dive into the world around you.